Dr. Alam, would you like to introduce your student?
Absolutely. This is Ms. Nidhi Chauhan. She's a computer information systems major. Her concentration is data science. Last semester she took a predictive analysis with me. That was a data science course, and this project came out of that course.
Thank you so much. My name is Nidhi Chauhan, and I major in CIS, Computer Information Systems, and my concentration is data science, where I had opportunity to take the course called Predictive Analysis with Dr. Alam. And I'm here to start a project, a data-driven approach to 10-year coronary heart disease risk assessment. Let us see what we have. So let me introduce you to the data set. The data set comes from the ongoing cardiovascular investigation conducted in Framingham, Massachusetts. It comprises of 4,238 rows of data, and it includes a diverse array of demographic, behavior, and medical risk factors. Here is our dependent variable. This variable captures the 10-year risk of coronary heart disease. As a binary indicator, it reveals if the individual is likely to have a coronary heart disease in the next decade or not. We will uncover the potential factors that leads to this important outcome variable. Let's see what these are the key factors of our independent variables. It includes such as age, gender, and if they're a current smoker or not, the cigarettes per day they consume, and some medical risk factors such as heart rate, diabetes, and glucose, as you can see here. Okay, so the question arises is, why did we choose the logistic regression model? So the logistic regression model is well suited for predicting binary outcomes. As you saw in the previous slide, that our outcome variable is a binary. So that makes it an ideal choice of determining the probability of coronary heart disease occurrence based on the specific predictor variables in the dataset. This formula you see here represents the logistic function which models the probability of event happening as a function of the linear combination of predictor variables, beta 1 and beta 0. It ensures that the output probability is bounded between 0 and 1. So as the first step of our analysis, a data preparation was needed. Because we had missing values in the data set, we utilized in K-NN imputation, K nearest neighboring imputation, to address the missing values in the data set. This ensured that the data set is complete for our analysis. Then we balanced our data set because we had more negative cases than positive cases. So we retained all the positive cases, which was 644 records. And we sampled 1,200 negative cases for the balanced representation. Then let's look into to see the first step into action. So let me. Okay, there it is. So here we see our studio, and the first step is here. So let me So if we run this first step, we can first see our data set here, which follows as we talked about. So this is the view of the data set. And so what Cannon imputation does is it finds the nearest neighbor, and according to the similarities of the data set, and then it forms a cluster based on that and chooses the mean of that to include the missing values. And then we need to define how many clusters we want the data set to form. So in order to find that out, the optimal number of clusters we would like to form, I read the elbow curve here, which shows as the number of clusters here decreases, the sum of error also decreases. And when the number of clusters hits 5, it stays consistent. So it shows that the optimal number of clusters is 5. All right. So let's get back into our slide for the second step. So the second step involved exploratory data analysis to get some more deeper knowledge on the data set. In order to do that, I assessed in interpredictor correlation. It shows as a relationships between each predictor variables to another one. And then after seeing that, I created some the predictor effects visualization, where I created box plots to see how our numeric variables has an effect on the dependent variable. And I did that for each of the numeric variable. And then for the categorical variable, I employed in the chi-squared test, and that to see the relationship between the categorical variable and the dependent variable. And then for the further analysis, I did the data splitting for 70% for the model training and 30% for the model testing. And then I obtained numeric predictors relevant to categorical variables association. So let's see the steps, how these steps are implemented in R. Here we see, so I've already ran that part of the code. So let me show you what kind of box plot I was talking about. So here is the box plot for the age variable and a 10-year coronary heart disease, our outcome variable. As you can see here, as age increases, the likelihood of occurring of the 10-year coronary heart disease also increases. And then here's another one. On the other hand, we have the heart rate predictor with our 10-year coronary heart disease, which here you can see that there are not, the heart rate variable does not really show any significance to our coronary heart disease variable. So it is not very significant. So let's go back to our slide. And so for this third step, let me zoom on this. Okay, for the third step, we were ready for the model progression. So in here, I ran initial model that developed where I developed a model that included the variables that we saw in the previous step. We had the ones that saw a significancy for the model, and I included those variables as seen here. It was included of age, education, cigarettes per day, prevalent stroke, systolic blood pressure, diastolic blood pressure, and glucose. Then we found out that uh, the diastolic blood pressure and education did not really help. So we dropped the education and diastolic blood pressure due to the long effect. Then I ran a final model that included the variables as you can see up above. Here we ran a full model comparison conducted in negative 2-log likelihood test comparing the full model with the reduced version of the identity influential predictors. There's no such thing as errors in logistic regression, unlike multiple regression. So what we do this, the parallel idea here is that we reduce the uncertainty by comparing each model to another one. Then I ran a bidirectional stepwise refinement model. What it does is it iteratively adds and removes the predictors based on the significance of the model to achieve the refined and robust model. Finally, I ran the model with standardized data. With the standardized data, it assesses the variable magnitudes and improves the interpretability and robustness of the model. Let's see how this is done in R. So first I ran the null model to compare the model with something. The null model does not include any variables. And then initial model that included the variables that we first decided to keep. And as you can see here, it included this variables where we see that diagnostic PP does not contribute much and the education does not contribute much as well. Then we run a final model. With the predictors that we decided to keep, and then a bidirectional, this final model, which we kept the variable that was shown significantly, statistically significant. Here we see how our model predicted how many output true negative and true positive, and which was about 70% of accuracy. And there are 62% of true positive and 71% of true negatives. See here. And then we run the full model with including all the predictors, all the variables. And we compare that to our final model with the only important variables that contributes the most. And as you see here, the accuracy rate is very similar to the final model. And here you see the similarities as well. And then we run this stepwise model, which also solves that it only keeps the variables that we included in the final model with a few extra ones, but that wasn't very significant to include, as you see here. And this is with our testing data set, the 30% of the data set we kept for testing. It also saw the accuracy of 71%, which was very similar to our model, our training data set. And then we finally ran our final model with the standardized data. And here we see that our model is a robust model because all of these variables are a great predictors and shows a statistically significancy, as you see here. Let's go back to our slide. So since we are done with the model, in the model we also saw this in R, where you see there's not a very much of a difference in the full model, stepwise model, and the final model, which indicates that our model was statistically significant. We saw that these are the variables that highly contributed to the occurrence of coronary heart disease, which are gender, age, cigarettes per day, prevalent stroke, systolic blood pressure, and glucose. This estimate shows the log likelihood of developing the coronary heart disease by the percentage on the right. These predictors include, as you see here, and this shows our model that it is a great fit. In conclusion, we can suggest that regularly monitoring the blood pressure and glucose levels is important. Because as we've seen here, as we've seen in the model, that those are the variables that was very contributing to the occurrence of the heart disease. And to embrace that, we need to also embrace the balanced diet and regularly exercising. And we need to incorporate stress management practices. And then consider smoking and quitting smoking or reducing is also very crucial. And we need to encourage medication adherence to those with specific medical conditions. So there are some limitations. In addition to these are the additional predictors that should have enhanced the model performance if we had this in the data set. Those include genetic factors. So So inclusion of the genetic markers and the family history data could provide a more personalized understanding of the individual's risk. So it could have been a better predictor as well if we had that. And then the another one is environmental factors. The factors such as air quality, proximity to green spaces, and exposure to environmental pollutants could have influenced the cardiovascular health. And physical activity patterns such as exercise intensity, frequency, and duration, as well as inactive behaviors, could offer a more better understanding of the relationship between activity levels and coronary heart disease risk. So overall, our prediction was good, and it was a statistically significant and robust model. And I really appreciate everybody to come here and attending, and thank you so much.
Time for maybe one. All right, well, let's thank our speaker again.